Yeah, I think it's about time for us to get started then on our next talk. So this talk is by Shreya Arora and Bruce Kessler. This is on detecting gerrymandering with computational algorithms. So you go ahead and get started.
Okay, hi, good morning. My name is Shreya. I'm a senior at the Gatton Academy, and I'm working with Dr. Bruce Kessler from the WQ Department of Mathematics, and together we are detecting gerrymandering using computational algorithms. So to start off, I'm going to explain what gerrymandering is. So it's basically the manipulation of district boundaries in order to establish an unfair political advantage for a particular party or group. And so to further understand this, here's an example where we have 50 people and 60% of them are with party orange and 40% of them are registered with party purple. And so what we're trying to do is fairly split them up into 5 districts. So in a fair districting plan, you would have results that are proportionate to the actual registration statistics. So this means having 3 of the districts go to the orange party and 2 of the districts going to the purple party, just because that aligns with the percentages of voters. However, in a gerrymandered districting plan, you would have results that are not proportionate to the actual statistics. So this means that there could be a district with all 5 winning party orange, or somehow the purple, who is once a minority, would somehow get a majority of the district seats. So just with gerrymandering, it's creating an unfair advantage for a particular party or group. So the federal government has tried to combat this by creating some rules for redistricting. So this focuses on having an equal population in every district, having contiguity. So this means that the district needs to be connected in some way. So you don't want fragments separated and just having all of the precincts grouped together. Then next is political boundaries. So you want your districting to follow city lines, county lines, and other political boundaries. You also want the districting to be compact. So just like looking at what's nearby and not creating a very stretched out district, but actually making it fair to what's nearby. And then also looking at partisan outcomes, which we just touched on a little bit, and looking at the actual voter statistics. And so then also another word I'm going to use a lot is electoral precincts. And so these precincts are the smallest unit of division that the government has. And then these precincts are grouped together to create districts. And then districts are what provides the representation in a legislative body for all the people within the precincts and the district. So Dr. Kessler and I worked to create a computational solution using Wolfram Mathematica. We developed a random walk model that generates thousands of districting plans. These district plans continue to meet the criteria regarding population bounds and precinct adjacencies. And then once we created these plans, we analyzed them to find normal distributions and find what the number of districts should be in for what party. And so this is an example of what a random walk model looks like. So basically each step is randomly generated, the size and direction. So it's just like not decided beforehand, and as you go through, it's different every single time. So in order to model our algorithm, Dr. Cusson and I created a model state known as Pentucky. And so it has 100 precincts and 100,000 people, and each precinct has a different population, but they're very similar. Then we created registration statistics for each of these precincts. So for example, precinct 1 with 1,000 people will have 40% registered with party A and 60% party B. And another example would be precinct 3 with 900 people would have 65% party A and 34% party B. So then in the images below, we can see that we have the precinct map for Pentucky. So there's 100 precincts, and then on the right side, you can see the majority based on the color. So for example, precinct 1 was the majority for party B, so it's colored yellow, and then precinct 3 had a majority for party A, so it's colored blue. And then this is important when we're generating the districting plans. So here are 2 districting plans that are gerrymandered. And so with the first one, we see that party A is winning all 6 of the districts, which is just, as you could see before, and we'll talk more about this later, not as proportionate as it could be. And then we also are looking at districting plan 2, where party B wins with 4-2 of the districting. And so we just saw that, and party B is much at a minority. So obviously this is not properly split up. And so another important thing are adjacencies. So this is looking at the precinct surrounding every other precinct, because we want to make sure we're maintaining contiguous districts so everything is connected. So we have to look at what districts are nearby each other. So for example, it's kind of small, but precinct 1 is adjacent to precinct 2 and precinct 4 because they're touching. And so we have just a table of everything that is adjacent to every other precinct. And so then for precinct 2, we also have that it's adjacent to 1, 3, and 4. An important thing to note here is that when precincts are touching at just a corner, that does not mean they're adjacent. So for example, 3 and 6 are not adjacent to each other, because putting those in the same district would, if that is just the border, would not maintain the contiguous rules. So looking at the actual algorithm for redistricting, the first thing we had to do was find all of the swaps that are possible. So this means that looking at each precinct and finding all of the adjacent precincts that are in another district, because you want to swap your current precinct into another district. And then you want to narrow down to legal swaps. So you want to make sure that these swaps do not disrupt the population bounds. And then next, you actually begin going through the legal swap. So you randomly make one swap, update the districting plan, look at who is winning all of the seats or some of the seats, which party, and then you keep repeating this process tens of thousands of times. So here's a visualization of how the algorithmic swap would work. So let's say we're looking at District 1, which is the orange, and District 2, which is the yellow. So we're going to switch. We can see that 13 and 14 would be a legal swap. So that means if I switched precinct 13 into District 1, it would not disrupt the population bounds. So we would add 13 to District 1, remove it from District 2, and then recalculate the vote counter and see which party would win the districting seats, or the district seats, yes. So after running our results about 20,000 times for both districting plans, both of the gerrymandering ones, we have two results here. So for the first graph, we see that initially Party A won all 6 of the district votes. However, after about 20,000 trials, we got the average to be about 4.9. And again, for districting plan number 2, which initially started with Party A only having 2 of the seats, once we ran the trials about 20,000 times, we got a mean of 5 again. So we can see that according to how the precincts are arranged and looking at the voter registrations, the mean number of districts that Party A should have is 5 out of 6, meaning Party B would get the remaining district. And so the next steps that Dr. Kessler planned on doing is looking at actually applying this to Kentucky. So Kentucky currently has 3,692 precincts. So with Kentucky, we only had 100 that we had to find the adjacencies for. And right now we are working on obtaining the precinct maps for all of the 120 counties within Kentucky. And this is taking a very long time. We have to contact the city clerk for most of these counties and figure out how to obtain their precinct maps for them, either online or by scanning in a physical copy. And then we go through each precinct map, figure out which ones are adjacent, how they relate to other districts and their precincts, and then we record these in an Excel spreadsheet. So once we're finished with this, we're going to actually run the algorithm with Kentucky data. In the meantime, we're working on looking at prediction algorithms. So currently we're working on a Monte Carlo simulation, which means it's a random walk model, but we want to work on future methods that help us predict what's happening a bit more with less trials. So we tested this concept with Kentucky. And so we started all 100 precincts with 100% Party B. Then we would switch a single precinct to 100% Party A. And then we would run the swapping algorithm and recalculate how many wins each party has. And then we continue to repeat B and C in a random order of the precincts, switching it from 100% Party B to 100% Party A and seeing how that affects the vote counters and which party would win the majority of the districting seats. So this is our data, and you can see the fit line basically starts at 0. So for a long time, Party A was not winning any of the seats since the majority was in Party B's hands. However, as we continued going up, the Party A would win more seats, and then eventually Party A was steadily winning all of the seats, all 6 of the districts. However, another idea we also have is not looking at switching the precincts in a random order, but initially starting with a single random precinct, switching that to 100% party A, and then going out from there. So it would basically be a hotspot. Then we would look at all of the adjacent precincts, switch those one by one to 100% party A, then recalculate, and then just keep going out from there and see how that would affect the linear outcome and how we could use that to predict actual districting in Kentucky and then in other places as well. So that's all I have for today. Thank you. And if you have any questions, I'm open to answer.
Okay, thank you very much. Questions for our speaker?
I have one. How do you deal with independents or people that have no party affiliation, or even those who do but never vote?
Yes. So in all of our districting in our voter registration statistics, we had like a list of 3. So the first one was party A, party B, and then we had another, which was just 100% subtracted by party A and party B. So we did leave that option there.
Okay, very good.
And John, to add to that, the thing we're running into with real data is that the number of registered voters does not equal the population.
Mm-hmm.
So the population is used for the fairness of a swap, but it doesn't play into the calculation of who won the district. Yeah. And I should throw in the one thing that we neglected to do, and we didn't create this. We're actually looking at research from Moon Dutchin from Tufts, and we should have put that in there. They have an actual research group that studies this for state legislatures, and it's a major, and she's published many research papers on it. So we're not as original. we are trying to kind of do what she's doing, but we are trying to expand it to see if we can understand more about that kind of logistic curve and what dependencies that has on like average adjacencies in the state, the uniformity of the pockets of different voters, which has been a curious thing doing the states. It's funny, a lot of times the concentration of one type of voter seems to fall along county lines for some reason. A lot of times you can look at we've got a map that we're using for some of these that shows the concentration of voters as a color. And you can, in many cases, see the county outline for a particular color, which is interesting.
I imagine in many cases, people who think alike tend to live together.
Well, I guess, but I mean, many of those people that are voting one way, they'll live closer to people who are voting another way, but they still kind of behave with the county. And the other thing, and Shreya alluded to it, is this is really this is public. This is data that should be public,
But it's not.
but it's not. Many of these county clerks do not have this data, their precincts published on like a web page or anything like that. And we've literally had to have county clerks take a picture or pictures of precinct maps on their walls and send them to us so that we could figure out the adjacencies for these different precincts. And that's just horrible in this day and age for that kind of information not to be readily available. Now, some counties do it well. Jefferson County, for example, has an interactive web map where you can find precincts and so forth. And I won't call out any names in case somebody's from one of these places, but I mean, honestly, and you have to, we've also learned politically, don't mention gerrymandering. Shreya, do you want to jump in? You jump in here anywhere, Shreya. But
Okay, no, you've basically said everything, but it's really interesting. Sometimes they won't even have like a combined map for all the precincts. They just have each one separately, and it's like a puzzle that we have to put together and see how they would arrange their precincts, because we have to see which ones are adjacent, but they just have every precinct as its own map, which is not helpful.
We initially thought this had maybe been worked out and we wouldn't have to do it by one of the political parties, you know. And if they have, they feigned ignorance of that knowledge, or they simply don't have it. And I can kind of see that now that we started doing it. 3,700 precincts. If you have all those adjacencies worked out, that's very valuable information as far as being able to set up. If you wanted to, those initial cases of gerrymandering that Shreya used to start her random walkthrough there, that was just me goofing around and showing it to Shreya. It's like, look at this. And there's certain strategies, you know, you take pockets of one voter and divide them. And if you need more voters of one, you kind of stretch over to another pocket and grab them. And so you can kind of do that in a minor sense, but if you're really trying to pull this off from a computational standpoint, you've got to know what things are legal, what things are near each other. And so if you've worked that out for all nearly 3,700 precincts in Kentucky, I can understand not wanting to share that information now that we've gotten into it.
I got a question. Shreya, are you simulating everything in Mathematica?
Yes, we are using Mathematica and then exporting it to Excel to run the analysis of the data.
How long does it take? I mean, it's a huge data, right? Data set.
Sometimes it takes 10 minutes and then sometimes it can take up to an hour depending on how many times we're running it.
Oh, I see. And it's a standard Monte Carlo method, right?
That's what we're starting with right now.
Yeah. Thank you.
Other questions for our speaker?
So I'm kind of outsider here from econ, but I just posted, I sent Bruce a link to some districting data from California, and they have a lot of this stuff already together. 2000 geography, district borders, 2010 district borders, so you can see the changes, and they are in a fairly accessible format too. So you should be able to match in census populations with voter registration data. It's California, so it's huge, but it's in a pretty usable format.
Okay, I'll send that to Shreya. We would like to be able to run this on state, like a real state data. We're obviously, since we're in the state of Kentucky, we'd like to be able to run it here, and particularly with 2020 census data getting ready to be used. You know, we'd like to have it going when that, if any redistricting takes place. But
Other questions? Okay, if there are no other questions, then thank you very much for the talk.
Okay, so our last speaker for this session this morning is Mark Robinson, and he will talk on Newton methods for nonlinear optimization. Go ahead.
Okay, thank you. So I'm just going to quickly read through the abstract here, and then we'll get right into the discussion. So Newton's method and variations of it have proven useful in solving many problems in nonlinear optimization. and I'll be giving an introduction to these methods in this presentation. So we're going to start out at a pretty basic level. If people have heard of Newton's method, chances are they've encountered that in elementary calculus class. And from that standpoint, Newton's method is looked upon as a method for root finding, for approximating the solution of a nonlinear algebraic equation. So you're solving an equation of the form f of x equals 0, where f is a nonlinear function. So I have a simple picture here. You can imagine the blue curve right here representing the graph of the nonlinear function, and you're trying to find a 0 of that function. So you can see that corresponds geometrically to the x-intercept of the graph of that blue curve. And so what Newton's method is a linearization method. So what we do is we take the nonlinear function and approximate it by a linear approximation, specifically by the tangent line to the curve at a given point. So you notice this point that's indicated right here. We're actually going to look at the tangent line to the graph of the function at that particular value of x, and that is the purple curve in here. And so our solution to the nonlinear equation is approximated by the solution to the corresponding linear equation, where we take the linearization, the tangent line, and then set that particular function equal to 0. So you notice geometrically then that gives us the intersection of that line with the x-axis, which is then the next point right here. So that is a single step of Newton's method, and then we can simply repeat that process where at each step we go up to the curve, form the tangent line, and look at the point of intersection with the x-axis. And we iterate and hope that that generates a sequence which then converges to the actual 0 of the function. So let's suppose that f has a 0 at x equal p. So what we've done here is we've actually done a Taylor expansion out through the linear term, and then the last term that's written here is actually your corresponding error term. So f of x, x naught here is actually the point around which we're expanding. That would correspond to this point right here. So we have f of x naught plus f prime of x naught times x minus x naught. And then the error term, if we just go out to the linear term here in our expansion, is one which involves the second derivative at some intermediate value c over 2 factorial times x minus x naught squared. So if we drop that error term, then we have the following approximation statement here, that f of x is approximately equal to f of x naught plus f prime of x naught times x minus x naught. Now, if we actually evaluate that statement right there at x equal p, what we get is we get f of p on the left, okay, and then that's approximately equal to f of x naught plus f prime of x naught times p minus x naught. So all I've done there is substitute p for x. Now the fact is, though, that p, remember, is a 0 of the function f. So f of p itself is in fact 0. So if we move on to the next page here, you see this equation that's right up here is, or it's really an approximation statement, that f of x naught plus f prime of x naught times p minus x naught is approximately 0. Now, what we're interested in, of course, is what is p. So if I replace the approximation symbol there by equality and replace p by x1, x1 is going to be our next approximation according to Newton's method. So all we need to do here is then solve for x1 in terms of all the known information, which is very easy to do. And so we just subtract the f of x naught from both sides. That gives us this next equation. Divide both sides by f prime of x naught. Obviously, that needs to be non-zero in order to be able to do that. And then we get x1 minus x naught is this ratio over here. And then finally add x naught to both sides. So then what we have then is that our first approximation, or improved approximation, we start with an initial approximation of x naught. Our first calculated approximation is the prior approximation minus then this ratio of the function evaluated at the prior approximation divided by the derivative evaluated at the prior approximation. So that's one step. That's your first step. If you just iterate according to that, you get the general method as illustrated below. So you're starting with an initial approximation and then iterate in that the new iterate is the prior iterate minus f at the prior iterate divided by f prime at the prior iterate. And so that's Newton's method for approximating a solution to a nonlinear algebraic equation. So of course, the title of this presentation had the word optimization in it. You know, you're looking for maxima or minima, something like that. So how does all this relate to that problem? So that's what we're going to turn to next. So you can apply this to an optimization problem of this type. Say you're interested in minimizing some nonlinear function f of x. Now, if you think about in a calculus course, right, you're trying to find maxima or minima, what do you generally do? You say, oh, I want to find where the derivative is 0. These give you the so-called critical points, and that may be a beginning step to finding local or relative extrema for a given function. But of course, as we well know, right, a critical point where the derivative is 0 could correspond indeed to a local maximum or a local minimum, but possibly neither one. So I've illustrated those three possibilities in this picture right here. However, if the function f has certain special property, namely that it is strictly convex, which in the parlance of elementary calculus courses would be concave upward, then we have a picture that looks like this. In that event, we'd have a single critical point, and that critical point would in fact correspond indeed to a global minimum for that particular function. So in this special set of circumstances, finding the critical point and finding the minimizer for that function would actually be equivalent problems. So what does that mean then? Well, for minimizing such a function, that amounts to solving for the critical point, that means solving the equation f prime of x equals 0. But notice that this is exactly the kind of problem we confronted when we first encountered Newton's method, right? We had some nonlinear function equal to 0. We're trying to find when that is the case. So all we need to do here then to apply Newton's method to the present circumstance is try to use it to approximate the 0 of the function f prime. And so what I've done is just reproduce Newton's method, replacing f by f prime everywhere. And so you get that you have an initial approximation, and then each subsequent approximation is found from its predecessor by taking the predecessor minus, and here's this corrective term here, f prime at the predecessor divided by f double prime. Okay, so just replace f by f prime because we're solving f prime equals 0 instead of f equals 0. So that's the situation in single variable case. What we're really interested in, though, is the multivariable case. What happens when you have a function of several variables? So to do that, we're going to jump into the multivariable framework here and do the same thing that we did for the single variable case. We're going to begin essentially with the root finding problem. In other words, trying to solve an equation of the form f of x equals 0. And then we're going to apply that to the corresponding optimization problem. So here I've written f of x equals 0, but you notice that the bold font here, right, we're talking about vectors. So the function f here, in this case, is actually a vector valued function of, in fact, a vector variable x. And the function f here is actually mapping from some subset of n-dimensional space back into n-dimensional space. The input into that x, right, is itself, it's an n-dimensional vector, and the output, f of x, is an n-dimensional vector, and it's composed of n component functions, each of which is a scalar valued function of the vector variable. So we have f1, f2, up through fn. And so this vector equation right here is just mathematical shorthand for a nonlinear system of algebraic equations, right? f1 of x equals 0, f2 of x equals 0, and so on. And so we're into the problem solving nonlinear systems of algebraic equations. Well, it happens that you can actually derive a Newton's method for this circumstance as well. And in fact, the mathematical formulation that is very similar to what it is in the single variable case. So you start with an initial approximation vector, and then you iterate according to this scheme right here. So each new approximation is its predecessor minus what? Well, remember before we had f over f prime, right? Well, we have the higher dimensional analog of that here. There is the function f, right, evaluated at the prior iterate. And then in front of that is the inverse of this matrix, J sub f, which is actually the Jacobian matrix of the function f. And that's an n by n matrix where the ij entry in that matrix is the partial derivative of the ith component function with respect to the jth independent variable. Okay, so you can clearly see here that if n is equal to 1, this whole thing collapses back down into the Newton's method that one learns in Calculus 1. All right, so this is the multivariable Newton's method for the root finding problem. Let's now look at the corresponding optimization problem and what the method looks like there. All right, so in this case, we're interested in, for instance, minimizing a function f of x. Now, this function f and this function up here of different character. Okay, this function up here, this big F, was actually a vector valued function of a vector variable. Big F mapped from a subset of Rn into Rn. The function little f here is actually mapping from Rn into R. Okay, so this is a scalar valued function of n variables. Okay, so that is the optimization problem that we're interested in. Okay, well, it happens that in a special case where this function is strictly convex, now remember we did that back in the one-dimensional case, that's where it was, you know, concave upward, right? If we have a situation where this particular function is strictly convex, then we actually have a global minimizer that can be found by using a version of Newton's method. If this function is strictly convex, then this Hessian matrix here corresponding to the function f is positive definite. All right, what is the Hessian matrix? It's an n by n matrix where the ij entry in that matrix is the second partial of the function f with respect to xi and xj as shown here. Okay, so if we do have a strictly convex function f, the Hessian matrix is going to be positive definite. I've given you a quick parenthetical definition there. And we also have a global minimizer. And where does the global minimizer occur? It occurs precisely where the gradient of that function f is 0. Now, the gradient vector is an n-dimensional vector where each component in that vector is just a partial derivative of the function f with respect to one of the independent variables. So, you know, we're interested in where is the derivative in a sense equal to 0, right? Where is the gradient vector actually equal to the 0 vector? But notice that what this is just another nonlinear system of equations to solve, right? So we're doing, notice I did everything in 1D, right? And now we're looking in higher dimensions, but you notice how things follow through in a parallel fashion. Okay, so this is then just applying the Newton's method. Let me just go back to the previous screen here, right? This is what the method is, right? We just have to plug all this in, where the capital F in this case is actually going to be the gradient of the little f. And then, of course, we have the Jacobian matrix, right? It's the Jacobian matrix of big F. Well, what's big F? Big F is actually the gradient of little f, right? Well, what's the gradient? What is the Jacobian of the gradient? It turns out it's the Hessian, okay, of the function little f. So then what you'll see next is I'm just going to reproduce Newton's method, and there it is for nonlinear optimization in a circumstance like this, and we've just made all the appropriate substitutions. So remember what it was in the single variable case, right? The new x was the old x minus what? It was f prime divided by f double prime. Well, you can see this is the higher dimensional analog of that. And so here we have each new iterate is the prior iterate minus, here's this corrective term here, right? You've got the gradient of the function evaluated at the prior iterate and then pre-multiplied by the inverse of the Hessian function or of the Hessian matrix. Now, of course, actually in practice, when these methods are implemented, you're not actually inverting this matrix and multiplying it by that. You're actually solving a linear system of equations, okay? But symbolically, we can write it in this format. So that is the method. Now, if you actually had a situation where you had a strictly convex function, then this would actually, this sequence of iterations would converge to the minimizer. You can nonetheless still apply this method even in circumstances where you don't have a strictly convex function. You just have to be in a region around the minimizer where locally you have a strictly convex function, or you can make various modifications to the method also. So I'm going to do an extremely elementary example. When you see this is sort of a classic example. You would find this example or one very much like it in a multivariable calculus book when you are dealing with the question of optimization, right? Finding maxima and minima for functions of several variables. So here, very familiar example here. We have f of x1, x2. I think in the graph it says x and y, but that's what x1 and x2 are here. Where we want to minimize the function f of x1, x2 equals, and you see you have x1, x2 times this e to the negative x1 squared minus x2 squared. And I use this example a lot when I teach multivariable calculus. It's a nice example to illustrate optimization in for a function of two variables, because we actually here, what you do in this kind of problem is you're seeking, of course, the critical points, right? Critical points then are actually where the gradient is zero, right? Where your partial derivatives with respect to x1 and x2 are simultaneously zero. And you end up in this particular example with 5 such points. And 2 of those, these 2 right here, which correspond to these points on the graph on the surface, right? You actually have local, in fact, absolute as it happens, maxima, and then you've got a couple of local minima here, and then you have the one in the middle here that's actually a saddle point. So again, illustrating critical point could correspond to a local max, a local min, or neither one, just as it was in the simple one-dimensional case we looked at before. So I'm going to show you some iteration or an iteration here where I started with a particular initial approximation, and then we get fairly rapid convergence to actually the minimizer that's over here in quadrant 4. Okay, so and that's the square root of 2 over 2 negative square root of 2 over 2. Started with this particular point. And the starting point is important because notice this is not a problem where we have a strictly convex function, right? So if I just pick an arbitrary starting point, this iteration could go anywhere. I mean, it could converge to this particular point of interest. It could converge to one of the other critical points, or it could diverge, right? I mean, we really have no guarantee there. Now, if I start in a region sufficiently close to this critical point, within which we have actually a positive definite Hessian matrix, then I'm going to be getting convergence to this point. And in fact, this starting point, it's possible to do an analysis to determine where that region is around this critical point. But this starting point is in there, and it does in fact converge. And I think we can all do square root of 2 over 2 in our heads, right? You can see that after 5 iterations here, we're pretty much getting a very good agreement with the actual value. I need to explain my picture down here so you understand all these different colored lines here. Of course, I think it's pretty obvious what the points are. But the blue curves right here, those are the set of points in the plane where the partial derivative of f with respect to x1 is 0. And then the yellow ones or orange ones are where the partial derivative of f with respect to x2 is 0. In order for the gradient to be 0, right, both of those partials must be 0. So you're looking at the intersection of blue curves and yellow curves. All right, and you can see where those are. There's one right here, right? There's another one right here. There's one down there. This one, the one we're interested in, is right here. And of course, the one in the middle corresponds to the saddle point that's right there. Okay, so that's an explanation of what this background here is. And then you can see we started with this point right here, and I think the iteration proceeded over here, and then very quickly in toward the actual correct value. So what I've illustrated here is I've actually illustrated just the basic Newton's method. I want to say a few things about some modifications of the method. And I made a statement at the top there: to be guaranteed to converge to the minimizer, you should start sufficiently close to the minimizer in a region in which the Hessian is positive definite. There are some modifications that are possible to the method. If at a particular step the Hessian is not positive definite, you could replace it by a small corrective, corrected version. And so here what you're doing is you're adding on, this is actually a scalar multiple of the identity matrix, right? So you're going to be perturbing your diagonal entries of that Hessian, where mu k is sufficiently large that the modified Hessian is positive definite and reasonably well conditioned. And then if you have a positive definite Hessian or modified Hessian, then your Newton direction, that the direction in which you're moving, is actually going to be a descent direction. That is important, right? Because here we're interested specifically in the value of the function going down, right? So we want to move in a descent direction, a direction in which the value of that function decreases. There's some alternatives if it's difficult to come up with analytic expressions for your entries in the Hessian or the gradient. Then you could use finite difference approximations to replace those analytic derivatives. There are some issues you could run into with that, particularly with the gradient. So it's best to use the analytic ones if you have those available. There's also the use of backtracking. Okay, you could actually start to take a step, see, are you really descending, right? Is you really moving in a descent direction? If not, you can maybe back up, maybe cut your step size in half, and then take another step in that direction so you're not overshooting, right? Not overshooting past where the minimizer occurs. And you could also couple the Newton's method with a global method, something like, say, a steepest descent method, and get a quasi-Newton type method. And here you might start with first a Newton step, but if it's not proceeding the way it should, if it doesn't look like you're moving in descent direction, then switch over and take a step using a different method. So there are combinations where you can work with the Newton method in tandem with other methods. And then secant methods, just like you think back to Calculus 1, you talk about, well, maybe you may or may not have talked about this in Calculus 1, but Newton's method, we're using the tangent line, right? Secant methods where you're approximating a nonlinear function by a secant line. So in the secant methods, you're actually using some kind of secant approximations to the Hessian. And so these are all different modifications that are potentially available to one to just the basic Newton method. So finally, then I just listed 3 different references, particularly the first one that's listed there, that's sort of a classic reference on methods for Newton methods, or other methods for that matter, not just Newton methods, but that's primary one in there, for unconstrained optimization and nonlinear equations. And then also referenced by Kelly about linear and nonlinear equations, and the Ortega reference that has a lot of worthwhile information about the multivariable Newton's method in it as well. Okay, so that's my presentation. I'd be happy to take any questions anyone might have.
Okay, let's thank the speaker for a very nice talk.
Yeah, thank you.
You can also put the reaction, John. Any questions for Dr. Robinson?
Do we know anything about the order of convergence in the higher dimensions?
The order of convergence for Newton's method is second order convergence.
Even in higher dimensions.
Even in higher dimensions, yes. It's amazing how much of the theory, and this is something I've looked into myself that I was interested in, about how Newton's method, primarily in the context of solving the nonlinear systems, right? But obviously with relevance to the topic here. But you can get degraded convergence, something you may encounter. Certainly people take a numerical analysis course, they learn this, that if you have what's a zero of higher multiplicity than 1, right? That's where, for example, if you think about y equals x squared, right? And you're looking at, all right, 0 is a 0 of that function, right? But it's a 0 of multiplicity 2. And actually, the graph is tangent to the x-axis there, right? If you try to approximate that 0 of x squared, namely 0, using Newton's method, you do not get quadratic convergence, you get linear convergence. Okay, and in fact, if you have a 0 of higher multiplicity, in general, Newton's method, which is normally quadratically convergent, which means basically that as you move through the iterative procedure, the error at each step looks like a constant times the square of the error at the previous step. So that gives you an idea of the rapidity with which the errors go to 0 as you proceed. Linear convergence would say, oh, well, as you go through the iterations, then the error at a given step looks like a constant times the first power of the error at the prior step. So obviously that's slower convergence. And there's even just in the research analysis of what that constant happens to actually be. And it turns out that constant gets bigger and bigger and bigger as the multiplicity goes up. Okay, so you get linear convergence that's slower and slower and slower and slower. That's all in one dimension, but you have parallel theory to that in higher dimensions also. Okay, but in the ideal circumstances, you end up with quadratic convergence for the Newton's method. Now, if you start modifying the method, right? If you were to, for example, use maybe finite difference approximations for some of those partial derivatives, then you may get a convergence that's not at that same rate. So those are some trade-offs that one might encounter when one's trying to make modifications to the methods.
Any other questions for our speaker?
Mark, in numerical analysis, we teach modified Newton's method, but only in a single dimension, I believe.
Right. Right.
Is this same idea working well for multidimensional case? If you know multiplicity of the root in advance, I mean, can you successfully modify the multidimensional Newton's method?
I'm not really sure about that. I mean, certainly we do have that available to us in 1D, right?
Yeah.
Yeah. I might guess that there probably is a modification, but I don't really know for sure.
Okay.
I have another crazy question coming from me. So so for example, a polynomial with complex roots, this will keep flipping back and forth because the tangent line will be horizontal, right? X squared plus 1. Would that?
Oh, okay. Well, actually, of course, you can do Newton's method in the complex plane also, right? So,
so are you using like
everything here,
R2 or C, as R2 or as C?
everything here is real valued, okay? Yeah, but you can, of course, do Newton's method in complex setting as well, and you also get quadratic convergence there if you have a simple 0.
Oh, you do? Okay.
Yes.
I haven't seen that actually.
Yeah.
John, have you seen that, something like that?
No, but we have the same Taylor series if you think about it. So wanted to define it in terms of the first two terms of that, it would be quadratic.
Yes.
I think that's right. Also, I've forgotten my linear algebra. The fact that you wanted it positive definite was to make sure it was invertible. Is that why you wanted
Well, of course, if it is, it'll be invertible, but it's more than that. Actually, in the optimization problem there, the fact that you have positive definite means that if you move in the Newton direction, that will be a descent direction. Okay, because you remember we're not just interested in finding I mean, like in the case of solving the nonlinear systems, we want to know where is that nonlinear function 0, right? But in the application to the optimization problem, we're interested in minimizing, at least the way it was formulated here. So with a positive definite Hessian there at the Newton direction, which otherwise wouldn't necessarily be a descent direction, right? Would be then a descent direction, which is one of the objectives we have. Decreasing the value of the function as you progress through the iterations.
Okay, that makes sense.
Very nice talk.
Yes,
Any
it was.
other- Okay, so let's thank our speaker again. I never fail to enjoy Mark's talks.
Thank you, Mark.
Yes, thank you.
Very nice job.